And that. Oh. Are you watching everyone? Are you seeing what everybody's up to? Are you? You are, huh? You're just watching everybody, seeing what's going on. Okay, folks. Just a couple quick notes. There is going to be no quiz today because you had a test on Wednesday of last week. I posted an announcement on Blackboard and also sent out an email today associated with that announcement that there is a new bonus opportunity where you can earn another 10 points towards your final grade. Basically, I'll be collecting food for the Bear Food Pantry as part of my classes. And so you can contribute in that manner. I have already graded one page of your exams. I hope to have them all done by the evening. But I know I will get them back to you by Wednesday. And speaking of Wednesday, whether for this class or any other class, Wednesday is the W deadline for UCA. After that, it's either you'll get an A through F grade. So just as a note, any questions before I progress? If not, we're going to actually get into the next concept that we will be dealing with associated with chemical reactions. So prior to my departure, we started balancing chemical equations. Basically, we took either an element and a compound, two compounds, and we started combining these substances to make new materials, which is what chemistry is really all about. Is taking reactants, combining them to make products. And we talked about the fact that we have to follow the law of mass conservation, so we have to balance chemical reactions. Now, one key thing to note is anytime you see a reaction, that should be your first step, is to either balance it or at least make sure it's balanced. Yes, ma'am, I will sit back down. So we have an example here. Calcium hydroxide is used to neutralize acid spills. If you spill 6.3 moles of hydrochloric acid, how much calcium hydroxide is necessary? And I give you the chemical reaction of calcium hydroxide plus hydrochloric acid goes to make water and calcium chloride. Again, you see a chemical reaction, your first thought process should be, is it balanced? If not, I got to balance it. That should be the very first thing you go to. Is it balanced? If not, I need to balance it. In this particular case, this is not balanced. In order to balance this chemical reaction, you will need 2 of the hydrochloric acids and you will obtain 2 of the waters. Now, what does the coefficients of a balanced chemical equation tell you? When I see these coefficients, what you are looking at is another form of a mole to mole ratio. When you look at the coefficients of a balanced chemical equation, you're looking at another form of a mole to mole ratio. This, folks, literally says to neutralize 2 moles of HCl, I need 1 mole of calcium hydroxide. Basically, if there's no coefficient, the 1 is implied. Or it can be read for every 1 mole of calcium hydroxide that reacts, I can expect 1 mole of calcium chloride to form. So again, this is what it is. These coefficients are mole to mole ratios. We'll come back to the question, but I wanted to take a moment and just summarize where we stand with all of this. So you could have if you saw the word atoms, ions, molecules, that was your cue to use Avogadro's number. And in so doing, you would convert that into mole of material. If you saw grams, that was your cue. Whoops, well, it's okay. That you would be using the molar mass to convert that substance into moles. Now, once you have it in moles, you can convert from moles of, say, substance A into moles of substance B. And to do so, you will always use a mole to mole ratio. But now we have two places to find that mole to mole ratio. The first place is the formula if we're talking about an atom in a compound. The second place, which is the new piece, is the coefficients if two compounds in a reaction. That's the new piece, folks. All the rest of this we've already talked about, but this is the new piece. Once you converted it into moles of B, you can convert it into grams of B using the molar mass of B. Or you can convert it into atoms, ions, or molecules. Using Avogadro's number. So again, the only new piece though is if we're dealing with the two compounds in a chemical reaction, then the mole to mole ratio is going to come from the coefficients of that chemical reaction. That's the new piece of this puzzle. So let's look at this question that we had earlier. Calcium hydroxide is used to neutralize acid spills. If you spilled 6.3 moles of hydrochloric acid, how much calcium hydroxide is necessary? We have 6.3 moles of hydrochloric acid, and we have been asked for moles of calcium hydroxide. Just like before, because I see that I am dealing with two different substances, It is that piece that tells me I'm going to be using the mole to mole ratio as a conversion factor. And according to our coefficients of our balanced chemical equation, 1 mole of calcium hydroxide was required for 2 moles of HCl. The other pieces I see is mole and mole, which are already covered in the conversion factor. So I'm ready to start this problem. So I start with the 6.3 moles of hydrochloric acid. My first conversion factor needs moles of hydrochloric acid in the denominator. So I'm going to be using that mole to mole ratio. 2 moles of HCl will go in the denominator, while the 1 mole of calcium hydroxide goes into the numerator. The moles of hydrochloric acid had to go into the denominator so that the unit and the substance would cancel, leaving moles of calcium hydroxide. So when you do the math, you will get 3.15 moles calcium hydroxide. And if I'm recording this according to sig figs, my starting number has 2 sig figs and mole to mole ratios are exact values. So therefore my answer should have 2 sig figs. So I would have to record this. I would have to record this as 3.2 moles of calcium hydroxide. Let's look at another question. Let's go with what mass of zinc sulfide can be formed when 45.6 grams of oxygen reacts with excess zinc, whoops. Let's go actually what mass of zinc sulfide is needed to react with 45.6 grams of zinc of oxygen. And the reaction we're studying is zinc sulfide plus O2 goes to make ZNO plus SO2. I see a reaction. What is step number 1? Always. Check to see if it's balanced. In this particular case, it is not balanced because on the left-hand side, I have 2 oxygens. On the right-hand side, I have a total of 3. So this is not balanced. So the first thing I would need to do is to balance this equation. And to balance this equation, you're going to need 2 zinc sulfides, 3 oxygens to make 2 zinc oxides and 2 sulfur dioxides. Only once you balance this equation can you try to answer the question. So I identify what I was given. I was given 45.6 grams of oxygen. You identify what you want to solve for. I need mass of zinc sulfide. So in other words, I want grams of zinc sulfide. Now we start tearing this thing apart. The first thing I see is I have 2 different substances. Anytime I have 2 different substances, I'm going to require a mole to mole ratio. In this particular case, there is 2 moles of zinc sulfide that is reacted with 3 moles of O2. That comes from the coefficients of the balanced chemical equation. The next thing I notice is I have grams of O2. I see grams, that means I'm going to need the molar mass of O2. We have 2 oxygens at 15.9994 each. Which means we have a molar mass of 31.9988 grams of oxygen is equal to 1 mole of oxygen. The next thing I see is I have grams of zinc sulfide. Anytime I get grams, that's telling me I'm going to want the molar mass. I have 1 zinc. Zinc has a mass of 65.38. And I have 1 sulfur with a mass of 32.06. So zinc contributes 65.38, sulfur 32.06. Which means we're dealing with 97.44 grams of zinc sulfide is equal to 1 mole of zinc sulfide. Now that you've picked apart what you were given, what you want to solve for to identify conversion factors, now you're going to do the math. You have 45.6 grams of O2. Your first conversion factor needs grams of O2. And that's going to be the molar mass of O2. So 31.9998 grams of O2 goes into the denominator with 1 mole of O2 in the numerator. The grams of O2 had to go in the denominator so that the unit and the substance would cancel out, leaving moles of O2. You then use the mole to mole ratio. According to the mole to mole ratio, for every 3 moles of O2 that was needed, you're going to need 2 moles of zinc sulfide. The moles of O2 had to go in the denominator so that the unit and the substance would cancel, leaving moles of zinc sulfide. Now we can convert that into grams of zinc sulfide by using its molar mass. 1 mole of zinc sulfide is 97.44 grams, with the mole portion needing to go in the denominator so that it would cancel out. And you're left with the mass of zinc sulfide. Keying this into the calculator. You should get a value of 92.5686 grams of zinc sulfide. Now to figure out our significant digits. This is multiplication and division, so it's going to have the same number of significant digits as the measurement with the fewest. Our starting quantity had 3 significant digits. The mole portion of the molar mass is an exact number. The mass portion had 6 significant digits. Mole to mole ratios are exact numbers. The molar mass for zinc sulfide, the mass portion had 4 significant digits and the mole portion was an exact number. So the one with the fewest was 3 significant digits. So our answer should have 3 significant digits. So we should record this answer as 92.6 grams of zinc sulfide. Questions? Folks, hopefully you're seeing that this process is the same as what we were doing with Avogadro's number. The process is identical. The only change we've made is where our mole to mole ratio can come from. On a test, what I normally do is I'll give you an unbalanced reaction separate from the mathematical calculation. And that way, yes, you have to balance some reactions, but your calculation isn't based off of those reactions. I mean, off of those, balanced reactions. So you will have to do both just separately. Okay, let me give you one to work on. Okay. So what mass of potassium chloride can be formed when 1.855 grams of chlorine reacts with excess KBr given the reaction KBr plus chlorine goes to form KCl plus bromine. Yes. I'll be back. Okay, let's see how it's going. So you were given 1.855 grams of Cl2 and you were asked for grams of KCl. Because the two substances are different, you are going to need a mole-to-mole ratio, which came from the balanced chemical equation. According to the balanced chemical equation, for every 1 mole of Cl2, you could get out 2 moles of KCl. Because you were dealing with grams of Cl2, it means you're going to need the molar mass of Cl2. 2 times 35.45 comes out to be 70.90 grams for Cl2 is equal to 1 mole of Cl2. Because you need grams of KCl, it means you need the molar mass of KCL. 1 potassium at 39.098 grams and 1 chlorine at 35.45 grams means that KCl has a mass of 74.548 grams of KCl is equal to 1 mole of KCl. Then setting up the equation, you started with what you were given, which was the grams of chlorine. You then used the molar mass of chlorine, and with the molar mass, the gram portion had to go in the denominator so that the unit and the substance would cancel, leaving moles of Cl2. Then you use the mole-to-mole ratio, putting the moles of Cl2 in the denominator so the moles of Cl2 would cancel out. And then you use the molar mass of KCl, putting the mole portion of KCl in the denominator so that the mole portion of KCl would cancel out, leaving grams of KCl, and your answer would come out to be 3.901 grams of KCl. Questions? Folks, I do want to bring up a term. A new piece of terminology. And that term is theoretical yield. The theoretical yield is the maximum yield of a product assuming no side reactions occur. This 3.901 grams of KCl that we just calculated would be the theoretical yield of KCl from 1.855 grams of Cl2. Basically, folks, it's saying in theory, this is the amount I could make. In theory. But that theory assumes that no oxygen enters the reaction from the atmosphere and reacts with the potassium bromide. It assumes that every single little bitty crystal of potassium bromide reacts with the chlorine gas, and that there's absolutely zero Cl2 molecules or zero KCl particles left. It assumes perfection based off of your balanced chemical equation. Now, we actually never achieve perfection in a chemistry laboratory. There are a number of things that can go on that would keep us from achieving perfection in a chemistry laboratory. So it is next to impossible to get the theoretical yield. It's virtually impossible. So that's why we have what's considered a theoretical yield. I am not going to discuss it in this class, but in future classes, you will talk about percent yield, which works with the theoretical yield, but it also works with what's called the actual yield, which is how much you really got from the experiment. I just want to make sure that we have the foundation of this calculation, because folks, if you take college chemistry 1, college chemistry 2, organic chemistry 1, organic chemistry 2, and any other chemistry course, you will be doing this math in every single one of them. If you take general chemistry for health sciences, you will be doing this math in that class. And they will just expand on it slightly. But this is the basics for most of the math that is done with a balanced chemical reaction. Do you want another example, or do you want me to move forward? All those that want another example, raise your hand to work. Got a couple. All those that want me to go ahead and do a different type of problem and us start getting into concentration, which is tougher than this, raise your hand. Okay, most people want the concentration. This is, folks, the key to this is this problem is almost identical to what you were doing prior to the exam and what was on the exam. We just got our mold-to-mold from a different location now. That's all. And if you'll come see me, I'll gladly work some problems with y'all. Those that wanted more, I'll gladly work some more problems with you individually if you'll come see me. Okay, so let's move on. And what I'll plan to do on Wednesday is we'll have a worksheet that has some of these problems and some of the topics I'm fixing to discuss. That will also give us more practice. And it'll give you an opportunity to ask me questions. So, of all, I better not say it that way. Of the stoichiometry type problems, where we use a chemical reaction. The toughest type deal with concentration. So what I will be doing today and for the rest of the day, and then again on Monday of next week, the Monday of the following week probably, is we're going to be dealing with concentration. So let's talk about everything let me explain why we're going to spend so much time on it. The first thing we're going to do is we're going to simply determine the concentration of a solution. Starting with grams. Of solvent. Excuse me, not solvent, solute. The next thing we're going to do is we are going to determine concentration or volume for a dilution. The third thing we will be doing is we will be doing simple conversions involving concentration. And the last thing is we will be dealing with concentration and balanced chemical equations and stoichiometry in a problem. It's the last of these that's probably the most difficult. Okay, so before we get into too much of that, there's some more terminology we need to discuss. The first thing we need to do is talk about the terms solute, solvent, and solution. The solute is typically the substance that changes state of matter or is in lowest quantity. The solvent is responsible for dissolving the solute. And is typically in the largest quantity. The solute plus the solvent make the solution. Now, just an FYI, because we never really talked about it, we do have states of matter. And they are a solid, which we often represent as a lowercase s, a liquid, which I represent as a cursive L, so you can tell it's an L, a gas, which was represented with a G, and then and then aqueous, which is AQ, where aqueous means dissolved in water. Now, folks, solutions can actually be anything. I mean, you're breathing a gas solution. The atmosphere is 78% nitrogen, 21% oxygen, and approximately 1% carbon dioxide and other things. You're breathing a solution. In the example I just gave, the nitrogen is the solvent because it's in the greatest quantity. The oxygen would be a solute. Brass that makes up a bed frame is a solution. It is typically made up of zinc and copper, or zinc and silver. So it's made up of two metals. Now, who the solvent is and who the solute is probably dependent upon the color of the brass. But the most common type of solution is the aqueous solution. You drink an aqueous solution every day because your water is not absolutely pure. I don't care if it says pure. There's going to be ions dissolved in it or gases dissolved in it. Maybe not in large quantities, but there are. In the case of water, the water itself is the solvent and everything else would be a solute. So solutions can be anything. They can be a solid, a solid liquid, a solid gas. They can be anything. It's just two substances combined. Now, in chemistry, the most common unit for a solution is molarity. Molarity is represented with a capital M. and it is moles solute over liters of solution. Almost all concentration units, folks, is solute over solution. There's actually only one concentration unit out there that is not solute over solution that I can think of. Almost all of them are solute over solution. Molarity just happens to be moles of solute over liters of solution. Now, folks, not only will we be able to calculate molarity, but because molarity is moles solute over liters of solution, it is a fantastic conversion factor. And so it will get used as a conversion factor a lot. So what we're going to do at this point is we're going to go back to number 1. What concentration and in this class, if I say concentration, I'm asking for molarity. What concentration of NaCl solution can be formed when 3.275 grams of sodium chloride is dissolved in enough water to make 500 milliliters of solution. Okay, what do I notice? I notice that I've asked for the concentration. Concentration means molarity, which is moles, solute over liters of solution. Or in this case, it will be the moles of NaCl over the liters of solution. To get to the moles of NaCl, I will be using this grams of NaCl and converting it accordingly. So I'm going to convert the 3.275 grams of NaCl into moles of NaCl, which is going to require the molar mass. And I know I'm going to need that molar mass because of that grams. So I have one sodium at 22.9 something. And since I can't read what's up there, I will get mine out. I have one sodium. Come on, be nice. At 22.990. I have 1 chlorine at 35.45. So we're looking at a mass of 58.44 grams of sodium chloride in 1 mole of sodium chloride. So starting with that 3.275 grams of sodium chloride, I'm going to convert that into moles of sodium chloride using that molar mass. Which comes out to be 0.05604 moles of NaCl. I now have my numerator. It's 0.05604 moles of NaCl. I now have the numerator because that is what I originally needed. Now I need to get the denominator. And for that denominator, I need liters of solution. Looking back at it, I was given 500 milliliters of solution. So I just need to convert that milliliters into liters. $500 milliliters of solution. There is 1,000 milliliters of solution to 1 liter. That is another way to do it. Or you can take that 500 milliliters of solution, and if you're using the original conversions I gave you, it would be 1 milliliter is 1 times 10 to the minus 3 liters. Either one would give you the same answer, which comes out to be 0.500 liters of solution. So now, if I want the molarity, molarity is moles over liters. Specifically in this case, it will be the moles of sodium chloride over liters of solution. So that's going to be equal to the 0.05604 moles of NaCl. Over 0.500 liters of solution. Which comes out to be 0.112 molar NaCl. Yes.
Are you basing that off of significant figures in the molarity conversion or in the previous conversion?
I based it off of both because the 500 milliliters, well, so I was considering 500 to be an exact number there. So I was basing it off 3 significant digits for the 500. Folks, I'm not checking sig figs on this particular test. I'm checking to do the math. I usually, if I'm not doing sig figs, I usually keep 2 to 3 decimal places. Okay, let's look at one more question. And I use SOLN for solution. Again, the thing to note is that I've asked you to solve for the concentration. So that means you need to determine the molarity. So it's going to be moles of CO2 over liters of solution. There's a little less work to do in this particular problem. So moles of CO2. Since I have moles of CO2, I'm going to start with the grams of CO2 and its molar mass, which I gave you. 28.5 grams of CO2 can be converted into moles of CO2 using the molar mass. Which is 0.647, and I'm keeping extra digits just through the problem, 598 moles. I need the denominator to be liters, which is awesome because I already have liters. So that means I'm ready to do this math. So the molarity is going to equal the 0.647598 moles of CO2 over 0.750 liters. And that comes out to be equal to 0.863 molar CO2. Yes, molar is another way to say molarity. questions? So on Wednesday, we are going to do problems related to both the conversions that I started today with, as well as these molarity calculations. Depending upon how long those problems take, then I might get into the dilution. We will just have to wait and see. But I want to make sure we have time to practice, since y'all said that helped last time, or was helping. I will see you on Wednesday.